Before we can talk about electricity and circuits, we need to understand how electrons move. To understand that naturally, we need to look at magnets. Magnets play a huge part in your world. A magnet is any material capable of attracting ferromagnetic materials and producing a magnetic field outside of itself. Magnets have both north and south poles, and their magnetic fields exist between these north and south poles. If you break a magnet in half, you'll still have two magnets, each with its own north and south pole. Magnetism is the attractive or repulsive force caused by the motion of electrons in a magnetic field. These forces are why you've observed opposite poles attracting and like poles repelling. You've observed the basics of magnets, but now let's break down a couple of these concepts in greater detail. Magnets can attract ferromagnetic material. The word ferromagnetic starts with an Fe, and iron is represented with an Fe on the periodic table of elements. This makes it easy to remember that ferromagnetic materials are materials made from iron, nickel, or cobalt. This also includes some alloys or rare earth metals and some minerals such as lodestone. These are the only materials that can be picked up by a magnet. This is why, although we think of magnets attracting metal, they only attract specific ferromagnetic metals. This is because these ferromagnetic materials are attracted to the magnet's magnetic fields. In fact, these ferromagnetic materials can become temporary magnets. This is why you can connect a chain of paper clips from a magnet. The magnetic field is caused by electrons traveling from the north pole of a magnet to the south pole. This is what causes this magnetic force, these attractions and repulsions. The direction of the electrons determines the attraction of the magnet. The north pole has electrons moving away from the pole, so it is attracted to the south pole, where electrons are moving towards the pole. When the magnets connect, notice how the magnetic fields align. When the two magnets connect, they make one large magnet, similar to how cutting a magnet in half makes a smaller magnet. The magnetic field lines are closer together at the poles, therefore this field is stronger at the poles. The magnetic field lines are closer together at the poles, so the magnetic field is strongest at the poles. This is why, when I try to attract these paper clips, they're going to stick to the edges, the poles of this magnet. The Earth acts like a giant magnet because we have an internal moving core. We have our North Pole and our South Pole. Because we act like a giant magnet, we have electrons moving from our North Pole to our South Pole. This is how compasses work. Compasses are attracted and repelled to Earth's natural magnetism. Compasses typically point north, but the north end of the magnet is not attracted to the north end of Earth's magnetic pole. So instead, the part of the magnet in the compass that's pointing north is actually the south pole of that magnet. The south pole aligns with the north pole of the Earth, and the north pole of the compass's magnet is attracted to the south pole. Opposites attract, like repel. So far we've been talking about natural magnets. Ferromagnetic material can become temporary magnets, though, when they're lined up in a magnetic field. A magnetic field is the passing of electrons from one pole to the other. So if we take an iron nail and some electrons, we can work backwards to create a magnet or electromagnet. Electromagnets are temporary magnets created by moving a current around a ferromagnetic material. Natural magnets naturally exchange electrons from north to south pole. This battery creates a current which pushes electrons from one end to the other, creating the two poles. This is because as the electrons move along the ferromagnetic nail, they create a temporary magnetic field. So, electric currents can induce a magnetic field. The direction of the current informs the direction that the electrons are moving. So it informs the direction of the magnetic field and tells us which pole will be north, which pole will be south. Electrons move from north to south. This is why we say an electric current can induce a magnetic field. As we observe, an electrical current can create a magnetic field. So if we control this magnetic field using electricity, we can attract and repel magnets to create motion in a motor. This motor is spinning because it is constantly attracting and repelling natural and temporary magnets created by an electrical current. If we reverse this process, we can get a generator. Because of this relationship, if we have something such as wind or steam to spin the magnets, we can get electricity. This is because an electrical current can induce a magnetic field, and a magnetic field can create an electrical current. Moving the magnets moves electrons. This is because if you control the motion of electrons, you can create an electrical current.